this is me up here, and maybe I look very different with without a hat. But my story is I did my, for 6 years, did my bachelor's in computer science. It actually didn't take me the full 6 years. I started off doing psychology. I went to school in Toronto, in Canada. Started off in psychology. Then I switched degrees to urban planning. Did that for my second year. And then it wasn't until my third year where I heard about Web3. Actually, it was about blockchain. And it got me really inspired to study computer science. And that's what I studied for the rest of my years in my undergrad. So from essentially 2016 to 2020, I did my bachelor's in computer science. Then I went on to do some work in data engineering. In between then, through some internships and co-ops. I was doing some machine learning research for a startup, an education startup actually, and then proceeded to do some essentially customer segmentation or customer profiling. Using what we were doing is we would track people's location data off their phone, and we would essentially plan out and map out where they visited throughout the day, so we knew where they slept, who they slept with, what their commute to work looked like, and through that we were able to use machine learning to start making predictions on their behaviors and patterns. But that felt not so nice. It felt kind of gross, and I wanted to get back on track to do what I had set out to do in the first place by studying computer science, which was work in Web3. So around the same time, I was also completing my master's in software engineering with focus on AI, which was very in line with my data engineering work at the time. And in 2021, also while I was also doing many things at the same time, I started working at BTQ as a product manager. And this is where I first got exposure to post-quantum cryptography, which is essentially cryptography that defends against computers today, as well as computers tomorrow, being quantum computers. And at BTQ, I learned a lot, and that's actually the reason why I came to Taiwan. BTQ has a large office, or I should say, really a team of researchers here, about 30 researchers, mostly PhDs and doctorates. And yeah, it was essentially the place to come learn from the best people, and that's where that's formed most of the basis of this presentation today, what I've learned at BTQ. In 2023, I had the privilege of joining BZD, which I think is this granted me the opportunity to come speak to you guys today. So thank you, Jackie, and thank you, Lasha. And this year, I've taken a lot of the technology that we've looked at BTQ and created a new company as well. So, but that's a little bit more outside the scope. So let's stay on the topic of today, which is quantum computing plus crypto in the true sense of the word, which is cryptography, not cryptocurrencies. I think a lot of people, falsely misattribute it, but cryptography plus Web3 and the intersection between all of these. So why are we talking about quantum computing? Well, this has been an idea that's been around for actually several decades, but only recently has it really started to pick up in traction. In 2022, there was about $20 billion of investment across the world, mostly led by national governments, as this is a top national priority for them. And in 2023, the numbers just came in, and the investments into quantum computing has exceeded 34 billion. So it's a growing industry, and it's becoming top of mind for top-level executives and leaders from around the world. And the idea around quantum computing is that it can solve certain problems exponentially faster than the classical computers we have today. And while it's still not necessarily clear all of the applications that quantum computers can solve, one application is very clear, and it's unfortunately to break the cryptography that a lot of us use today. And we can explain a little bit more as to why and how that happens, but just to give some high-level kind of reference points. The projected timelines for breaking cryptography, they can vary, but there's a lot of research that comes out all the time. Last summer, there was a paper that came out of the French National Scientific Research Lab, and they are projecting that it takes 126,000 cat qubits to break 256-bit elliptic curve cryptography, which is essentially the cryptography that we all use today in many of our devices and and applications in 9 hours. And so that's a significant threat. So how long until we get to 100,000 qubits? And there's been, and there was a survey put out to several quantum computing companies around the world, some leaders in this space. And for example, IBM expects to have near 100K qubits by the end of the decade. Again, these are private companies, and they have, they're maybe being a little bit gracious with their projections because they need to make money. But the long story short is, very plausibly within the next couple of decades, we could have our cryptography broken by quantum computers. And just some other kind of peripheral media coverage around this. Well, most significantly from the White House, just to reemphasize how much of a national priority this is. The US White House has put out 2 memorandums. One is to enhance essentially their national quantum initiative, which is to increase investments into quantum computing and also to launch post-quantum cryptography standardizations competition, which will allow US companies and government to be secure against these quantum adversaries or attackers. Yeah, and that's essentially what we have on the right here. And then this idea has also swept major news outlets as well. So let's dive into, still at a relatively high level, but let's go one step down and look at what exactly are quantum computers and how do they work? Well, a quantum computer uses the fundamental bits are called qubits. So how in our computing paradigm today, we use binary bits. So all of the numbers that we encode and all the logical gates, these are all ones and zeros. So they're binary, one or the other. Qubits or quantum computers use what are called qubits. And these can essentially, they're very similar to a bit where you can be a 1 or 0, but it also has this special property where it can be somewhere in the middle. And this is called a superposition. So a superposition is a state where the bit is in a 0 and 1 at the same time. And not only can quantum computers use these qubits, but they can actually entangle several qubits together, which means that there are several bits which are in a quantum position, a quantum superposition. And essentially, their behavior are now related to each other. And so when you make a change to one qubit, it directly impacts another qubit. And essentially, this process of entangling qubits in superposition together, they're able to collapse to certain states that find solutions much faster. So these are just kind of the high-level principles of quantum computers, but we won't go into too much about the physics or the mechanics of how quantum computers work. We'll mostly focus on what are the implications of this new technology. So how I like to think about this is that currently we stand in the middle of 2 walls that are coming in closer towards each other. On one hand, we have accelerating quantum hardware, where the hardware keeps getting better and better and better, and we also have, as we have more money put into them. And then we also have algorithms like Shor's algorithm and other quantum algorithms as well, where breakthroughs are made every month, and essentially it lowers the cost of executing these algorithms on hardware. So you have improving hardware and improving algorithms, and this means that the D-Day or the due date for when we need to really strongly consider the threat of a quantum computer, that day is accelerating faster and faster. It's coming in towards us faster and faster. Okay, so we talked about quantum computing. The first and most perhaps serious use case of it is breaking the cryptography that we use today. So let's spend a moment just walking through how all this works. But maybe it's just like, for my understanding, how many of you are familiar with cryptography and private keys, public keys? Do you guys, is this new news? Okay, yeah. Old news, new news? Okay. So essentially in asymmetric crypto systems, in asymmetric cryptography, there's this notion of a private key and a public key. Now, this will differ from symmetric key cryptography, where there's only one key. And the problem with that is that if you want to share information with somebody else, you have to give them the key. And that's not good because you want oftentimes to keep your information private. So public key cryptography affords us the opportunity to encrypt information and only have kind of selective disclosures to who can actually read the information. And the way that public key cryptography works is that essentially you use some algorithm to generate the private and public key. And right now, these algorithms today rely on mathematical structures called elliptic curves. And actually, I can draw this on a board, and maybe it'll make more sense. Am I able to? Yeah, sure. Okay, cool. It just up right there, perfectly. Okay, so we've talked about using certain mathematical structures to generate the private and public keys. And the structure that we use today is what's called an elliptic curve. And it looks something like this. And now elliptic curves, they can vary in shapes and forms, but it gives you an intuition as to how we can actually generate a private and public key. So what happens is we use an elliptic curve and we essentially generate 2 points on it. One will represent the private key, and in cryptography we can use SK for the secret key. And then there's also the public key, which needs to be generated. Okay. And what this is supposed to do is we're able to multiply these 2 points on the elliptic curve in order to get a third point on the curve, which represents your signature. And how this is used in application is every one of us has our private keys. So for example, let's kind of bring it back to Web3 and say we have our wallet, our crypto wallet. Let's say it's MetaMask or Ledger. Now your wallet has your private key, and you don't want to share that with anybody else, otherwise they'll be able to have your crypto. So this is the first point on the curve. And when you want to make a transaction, let's say I want to send a transaction to Jackie, I will send my transaction and I will sign it with my private key. So I have a transaction, let's say, and I want to sign this with my private key. And this will produce a signature. And when Jackie or anybody else on the network wants to just verify that this transaction came from me, they can essentially merge the signature with the public key and verify that everything checks out. And so this is what the kind of like the points on the elliptic curve represent. It's a way to verify that a signature actually came from a private key. And the point is that this is supposed to be like a one-way function. As in, you're not supposed to be able to take a signature and a public key and then derive the secret key. In order to do that, you need to, or maybe I should say, the difficulty of doing this. It is theoretically possible, but using elliptic curve structures, the way to reverse direction would be to solve the discrete logarithm problem, which is intractable for sufficiently large prime numbers that we have today. And this is essentially what the quantum algorithms pose a problem to, is that there exists an algorithm called Shor's algorithm, which efficiently solves the discrete logarithm problem in an exponential time. So the more qubits you throw at it, the faster it's able to solve it. And this is why in the previous slide you saw kind of 9 hours to break 256-bit elliptic curve, which would previously have taken over like 10 million years to break on a classical computer. So this is really kind of the problem here using elliptic curves. Well, thank you. Great. Yeah. So we said the private key and the public key can be used to essentially produce a digital signature, and it's supposed to be a one-way function, but quantum algorithms break that, and using essentially using a public key, which is by definition public, a quantum algorithm could derive the private key. Okay. And what kind of implication does this hold for us? Well, a lot of people, especially now even institutions, are thinking and talking about Bitcoin as digital gold. Now, I'm not here this is no investment advice, so excuse that part. But if we envision a future where we can actually move our financial rails or financial infrastructure onto Web3, this has dire consequences in the face of quantum computers. If we're thinking about any asset as being, a form of gold or as being stable, it needs to be resistant against quantum computers. And this is really the problem that us at BTQ are trying to solve, and just cryptographers around the world are trying to solve. So just to kind of reiterate how secure Bitcoin is, and kind of like the lack thereof, you can see the exact same public key, private key signature mechanisms at place. Essentially, when someone transacts, they'll sign a transaction using the private key, produce a signature, and their public key is by definition public. And again, anybody on the Bitcoin blockchain, because these public keys are involved in the transactions, they can take the public key and then derive the private key, and then the account goes bust. So this is where post-quantum cryptography comes in. And post-quantum cryptography is really simple. It's just the same kind of security mechanisms that we wanted of cryptography, but it's you can think about it as securing a larger class of problems. If we think about it in computational complexity, there's like P at the core, and so we didn't want to encode any of our security, our cryptography using problems in P, because it can be solved in polynomial time. So we chose a problem outside of P, and this is where the cryptography we use today is. And then now that we have quantum computers, we want to again just move the problems that we use to secure our crypto systems to a computational complexity class outside of quantum computers. So we just kind of keep moving the problem outwards, if that makes sense. And so that's what post-quantum cryptography tries to achieve. So let's just assume that we've implemented post-quantum cryptography. And maybe I'll just spend a second here and talk about, why, how are we able to, how does post-quantum cryptography work? At a very basic level, we saw how elliptic curves rely on the discrete logarithm problem, and that can be broken by a quantum computer. So in post-quantum cryptography, you use different mathematical structures where there's no known efficient quantum algorithm for. So this could be kind of lattice-based problems, which rely on or I guess it's like the short integer solution problems or learning with error problems, and this is the family of lattice-based. You can use hash-based as well. There's isogenies, which are mappings between elliptic curves. It's really crazy, but those are essentially post-quantum cryptography, or in post-quantum cryptography, you just swap out the problem that you're assuming to be difficult in securing your crypto system. So let's just assume that we've done that. Then we've reclaimed the safety of our private keys, and that's all alive and well, right? So I think we're good to go. We're ready for quantum computers, yeah. Essentially, no. Essentially, no. Unfortunately, there's a lot of trade-offs that come with post-quantum cryptography, and most notably in the key sizes and signature sizes of these algorithms. So we talked about elliptic curve digital signature algorithm, right? So this is the algorithm that uses elliptic curves in order to generate the private and public keys. Well, the three on the right are the US standardized post-quantum cryptography digital signature algorithms. It's a mouthful, but essentially these are the quantum safe ways that we can generate private and public keys. And we can just see immediately that there's a huge increase in both the public key and signature size. And there's some problems with this, but let me just come back to the previous slide. And I think this is really cool because it's something that's happening in the world that a lot of people don't know about. But we've talked about how the US is standardizing these signature algorithms. So let's just visit that for a sec. So in 2016, the US government, well, it's really called NIST, which is the National Institute of Standards and Technology. And this is a department of the US government. It's a Department of Commerce of the US government. And in 2016, they put out a call for proposals for researchers and academics around the world to submit these algorithms that are quantum safe. And essentially, what they cite here is that in recent years, there's been a substantial amount of research on quantum computers, machines that exploit properties of quantum mechanics to solve mathematical problems that are difficult or intractable. Unfortunately, though, these quantum computers break many public key crypto systems, which is exactly what we talked about, including RSA, DSA, and elliptic curve crypto systems. Elliptic curve crypto systems are essentially just generalizations of RSA and DSA and are the most modern form of these algorithms. And due to this concern, many researchers have begun to investigate PQC, also called quantum resistant or quantum safe cryptography. And the goal of this competition, of this call for proposals, is for the US government to standardize certain quantum safe algorithms that can be used by the government and by US companies. And as we saw, these three algorithms were announced last year to be, they're going to be standardized. The US government is just going through and essentially the algorithms have certain parameters that they need to choose in order to standardize. And so they're going through that process right now. And they've also put out a call for additional signatures. So those three algorithms were standardized last year. And then also at the same time, they asked for additional signatures, additional algorithms to be submitted. And the reason for this is that the algorithms that were chosen, Falcon, Dilithium, and Sphinx, these two are lattice-based cryptography, so relying on problems coming from lattice problems, assuming them to be difficult. And then Sphinx Plus is a hash-based solution, and the government is just concerned that it's kind of like investing. You want to diversify as much as possible. If one stock goes down, or if one crypto system, if there's a breakthrough in breaking, let's say, lattice-based cryptography, then we want to have something else to fall back onto. Or that's what the US government is thinking about. And I think it makes a lot of sense. And so that's what this additional round or this round one of additional signatures is for. It's to diversify the standardized algorithms. And actually, the team here in Taiwan actually submitted an algorithm. So our team at BTQ, and I'm not sure if maybe you guys recognize some of the names here, but like Chen Mo and Po Chun, they're both NTU graduates and some of the most highly esteemed cryptographers here in Taiwan. But yeah, so we are currently competing in this NIST standardization process, and really interestingly, we're the only algorithm left in our category that survived. And what's even, I think, cooler than that is we are proposing the first ZK-based signature scheme, which is, yeah, maybe a little bit. It's kind of hard to think about. I can explain it. It is actually outside the scope of this, but I think it's really cool. Okay, yeah, so I'll just leave it there. So that's the whole NIST standardization process. Yeah, okay, and then again, the problem with these algorithms is that, especially in a blockchain setting, so like in a kind of a traditional corporate structure, like let's say a traditional kind of Web 2 structure, maybe this doesn't matter as much because you have really large servers who are facilitating, all of our Facebook messages to each other, and you have big banks working on coordinating those transactions. But if you bring this to a blockchain, this has tremendous consequences, right? So what we want to have is to be able to decentralize our infrastructure. And this involves, running nodes that you can run presumably on your laptop or, your PC and hopefully, inevitably, most likely one day on your mobile phones. And, what happens if with every transaction that's broadcasted across, let's say, a blockchain, that transaction needs to have a digital signature attached to it because you need to be able to verify who it came from. And what happens when the signature size 10x's from 66 bytes in ECDSA to 666 in Falcon to 2.5 kilobytes to yeah, right. It's just that it congests the blockchain, and the problem that happens here is that you're able to essentially fit fewer transactions into a block. This means higher latencies for users. It takes 10 times as long to have your transaction finalized. Also 10x higher transaction fees, which is always a problem in Web3. It's actually being solved really well right now with kind of dank sharding and Ethereum. But it is historically a problem, and essentially post-quantum cryptography reintroduces, or maybe it's better to say it loses all of our progress in scaling blockchains because we have this 10x increase at least. Okay, so how do we solve this? We've seen this problem before. It's like, how do you scale blockchains? Well, oh, sorry, one more slide. Okay, just to talk about kind of what the further research on the implications of quantum state cryptography. This is a study done by the Bank of International Settlements in Switzerland. So this is the BIS, is like the central banks of all central banks. So it's like the major, it's like the cornerstone of financial infrastructure. And they were also looking at CBDCs, which is really cool. Central bank digital currencies. So essentially kind of like digital, like NTD, things like that. And what they looked at was that kind of through two lenses, through duration of end-to-end payments and throughput, quantum safe cryptography is really damaging to blockchain experience. 5x, 5x increase in duration of end-to-end payments, and then 2 orders of magnitude fewer transactions per second. So this is a very significant problem. That is the problem of post-quantum cryptography used in blockchains is a very significant problem. Okay, so this is where some new types of cryptography comes in, and cryptography that's used everywhere, to be honest, in blockchains today, and we hope that it'll be also used outside of blockchains soon. But this is the idea of zero knowledge, ZK. I'm just curious, has anybody heard of ZK? Nice. Okay, good stuff. Okay, very good. So zero knowledge is essentially a new cryptographic primitive, which allows you to prove that some computation took place and to prove that it was executed correctly. That's kind of an abstract way to look at it, but we can look at it more concretely by saying there's some function x where you have some inputs. It could be just public, where everyone can see it, or you can also optionally add in a private input. And we essentially want to have a proof of knowledge that this function was run, was evaluated, or that some computation took place, that computation being the function. And it turns out that this is actually a really powerful cryptographic tool because it can essentially, you can think about it as compressing these large post-quantum digital signature algorithms on a blockchain. Now, what's the best way to demonstrate this? Okay, actually, there is this little game. It's called ZK Wordle. Are you guys familiar with Wordle, the word game? Essentially, what you're trying to do is you start off with like an empty grid, and then you guess a word, and then if the letter is yellow, it means that this letter belongs in the word. If it's green, it means it belongs in the word and it's in the right place. And what you're trying to do is guess the word sooner than all of your friends. So essentially, you're trying to it's like a gigabrain game. It's like you're trying to compete against your friends and say, I'm the smartest. I was able to figure out what word this is. And a really good demonstration of ZK, or zero knowledge, is being able to prove that you were able to solve solve the word to your friends. And this is something that's not traditionally enabled by like the original Wordle game, but somebody made a ZK version of this where you can solve the word and then have a cryptographic proof that you can show to the other friends saying, hey, look, I solved the Wordle, I solved ZK Wordle in, let's just say 5, or in however many tries. And so you can think about here the function being kind of like the rules of the game, and the output of this will be a cryptographic proof saying that I solved this. And so I'm just kind of curious if we put so I partially solved this, and I'm just kind of curious to see what happened. What do you guys think the word is? CR. So CRA. These are the correct letters in the right place. So is E. What could be? I'm thinking crane is like the logical one. Yay. Okay, we got it. Cool. Awesome. And so essentially this, what we have now is a cryptographic proof that we can share to others. We can actually post it on blockchain and say, I, with my private key, was able to solve, so the private key could be, or sorry, actually it would be a public key, because I would be committing using my public key to the blockchain. My public key was able to solve this word, with these statistics, in 5 tries, and then everybody else could verify that I was able to do this on the blockchain. So that's kind of like an interesting example of how ZK is used in practice. But ZK is so cool because it can really be used for a lot of things. And one of the ways that it's used right now, and probably the most popular way, is to scale blockchains. And the way that this happens is it takes essentially, so kind of historically, we've been transacting on blockchains, and just like the blockchains themselves, which are like, let's say, Ethereum or Bitcoin. And a few years ago in the Ethereum community, they came up with this idea of using ZK to essentially batch transactions together on a secondary layer and then post a validity proof to the L1. And so what happens is that now, if I wanted to send money to Jackie, I would most likely use something called a layer 2. And again, this is just it's literally like a layer on top of Ethereum. And it's another blockchain. And I would send my transactions to the layer 2. And what the ZK EVM is doing, the zero knowledge EVM, is it's executing all these transactions against the Ethereum virtual machine, against the Ethereum computer, which we would normally execute the transactions against. And so that's what the EVM is, the Ethereum virtual machine. And you can see that it's just kind of prepended by ZK, saying that this is a provable EVM. So we're proving that all these transactions were successfully executed against the rules of Ethereum on this layer 2. And that's why we can then just say, oh, a bunch of transactions were executed correctly against Ethereum, generate a zero knowledge proof, and then post that one proof to the to Ethereum L1. And this is how we essentially, the gas fees now get split across, let's say, 2,000 transactions. And then we're also able to fit 2,000 transactions into a single transaction on the underlying L1. So we're able to get a lot more scaling and a lot higher TPS this way. And so this is one way that the snarks are being used today. So another really nice example. Okay. Yeah, please. Yeah, thank you. Yeah. Yeah, so good. Great catch. So it's a misnomer. It's not correctly named ZK. Unfortunately, it should just be, you're right, it should just be a snark. Is that what you're kind of suggesting? Okay, yeah. Okay, so it's called ZK because it uses zero knowledge proofs. This being able to verify or prove that some computation took place. And so in this case, the proof would be that these transactions were executed against the rules of the Ethereum virtual machine, and then generating a proof of that, so that only that proof needs to be posted to Ethereum. So that's why it's called ZK. But zero knowledge actually implies that there's no knowledge about the kind of like the argument. And this is more complex. Maybe it's not. Maybe I'm overthinking it. But it should actually just really be called a snark, not a ZK snark, because there's no privacy involved in this. Zero knowledge implies that there's some privacy, whereas you can just use a succinct argument to. This is this validity proof is essentially this succinct argument that we're generating that says that all the transactions were executed against the EVM. And so, yeah, that's actually like a really big point of it's like saying crypto is like cryptocurrencies. It's just a misnomer. Yeah, most of the snarks today, or most of the ZK EVMs actually don't have any privacy, and so they should just be called like, but that it just doesn't roll off the tongue. It should be like snark VMs or something, or like something like that. But yeah, that's why they're called ZK right now, because they use zero knowledge, like the same kind of principles behind zero knowledge proofs without the actual ZK. They just use the snark part of it, if that makes sense. Okay, cool, thanks. Okay, so I think so we've talked about snarks now, and why did we start talking about snarks? Well, it was because we need to battle this explosion in key and signature sizes in blockchain. So let's bring this back. How can we use ZK in order to help us solve this scaling issue in post-quantum when we apply PQC to blockchains? Maybe I need to bridge why we want to do this. Oh, sorry, it's in the wrong button. Okay. So we can apply the same principle using these post-quantum signatures, or using zero knowledge applied to these post-quantum signatures. So we saw that the signatures in post-quantum cryptography are 10 times larger. What we can do is we can, similar to like how we aggregate these transactions, we can aggregate signatures and prove that they all checked out, and then generate an aggregate signature or a proof that all of these signatures are valid. And so instead of every transaction having their own signature that's posted to the chain, we'll keep the transaction data, but instead we'll aggregate over all these signatures, all these post-quantum signatures, digital signatures, and generate a proof of knowledge that we can then post to the blockchain. And this essentially, once you use enough signatures, our team has demonstrated that, using like 2,000 post-quantum digital signatures, you essentially, when you post it to the chain, it's the same size as a single ECDSA signature. So you essentially negate all of the negative consequences of post-quantum cryptography. Yeah, please. Yeah.
What's the use case of ZK today in the real world? Like game or
Yeah.
daily life or
Yeah, great question. Yeah.
How would you describe ZK in simple one word?
Yeah, so back to your question about like why use ZK? ZK is typically associated with some sort of privacy, zero knowledge about some argument, and a real world use case today, and something you're actually working on, is identity, where you can actually generate proofs of your identity and have someone else verify that, let's say you're a Taiwanese citizen, or I'm a Canadian citizen, or maybe a US resident, without actually disclosing all of your personal information. Instead, how it would work in the real world is you would perhaps scan your passport, and then you would generate a zero knowledge proof of knowledge that, on the scan you have a Canadian citizenship or Taiwanese. Yeah.
So you don't read everything. So how it can work?
Yeah, exactly. Yeah. So there's there's called a prover and a verifier. The prover generates the proof of knowledge, and then there's on the other, in order to kind of verify this, there's another cryptographic tool which it's essentially used by, like in the case of identity, it would be used by like a government agency, where they know that, according to like this program, as long as this zero knowledge proof checks out, then the statement in that argument is true. Yeah. And that's the idea, is that like we're trying to omit as much of the hardcore evidence in order to have these privacy benefits, these privacy guarantees. Yeah. Okay, well, thank you. I think for the question. Okay. So yeah, the idea is to try use snarks in order to scale post-quantum cryptography. And if we do that, then we also need to make sure that we use snarks that are also post-quantum, because again, they're just another form of cryptography. And actually, most of the ZK snarks we use today are based off of the same elliptic curve cryptography. So that's not good. So let's see, how do we generally build snarks? So let's say we want to build a snark. There's like two major ways. One is using what's called a polynomial interactive oracle proof plus a polynomial commitment scheme. And another way is doing a polynomial commitment, or sorry, probabilistically checkable proof plus pairing-based cryptography. But we don't want to use any pairing-based cryptography because that implies some sort of elliptic curves, which is vulnerable to quantum computers. So we can just scrap that out. And so we're left on this left part of the tree. And really, you kind of, if you look at this kind of like middle layer, you can see that all of the quantum vulnerable primitives that are being used are the discrete log based and pairing based. So you actually, when you build or when you use a polynomial commitment scheme approach, it's called a polynomial commitment scheme, you actually don't want to use anything that relies on these. So you can use, just there's like different kind of ingredients that you can use in order to construct these quantum safe snarks. And the idea is that, it's possible. We've demonstrated this and they're feasible in practice, but there's just a much smaller design space. And with that, we have fewer, how do I say this? Yeah, our trade-offs are more severe because we don't have as many options to choose from. And so what we're stuck with are snarks that are based off of essentially like interactive oracle proofs plus polynomial IOPs in order to construct the snarks. And then you also have what are called starks. But that's also outside of the scope of this. So let's just say that quantum resistance is possible, where we can essentially use post-quantum cryptography plus post-quantum zero-knowledge proofs in order to compress them down. But we just need to build it, and there's still a lot of work to be done here. So let's try bring this back into practice again. So let's think about, okay, like, what are all the different opportunities to use this Web3 technologies in things like CBDCs? And this is a map of all the different CBDCs, central bank digital currencies, that are going on around the world. And you can see that every country, or almost every country, is developing and researching CBDCs. Many are in the research phase, and some already have a proof of concept, including my home country of Canada. That's a good question. I don't know which country that is, but yeah, we should look into that. Yeah. And the idea is that, okay, well, if we're going to have a future with these quantum, if we're going to have a digital asset future, we need to not only use post-quantum cryptography and things like, maybe that we can have post-quantum Ethereum, maybe we even have post-quantum Bitcoin, and we can even think about, how do we replicate a lot of the financial infrastructure that we have today. So some ideas that our team has been playing around with is one, which is Bitcoin Quantum, where we can actually substitute the proof of work mechanism with a quantum problem in nature. I should partition these two sections, by the way. This is so we talked a lot about the post-quantum cryptography stuff, and I think I gave an intuition as to into that is feasible and that we just need to actually now construct it. But when we start, and so this section is now focused on applications of of both post-quantum cryptography and quantum computers. So yeah, in this idea for Bitcoin quantum, you essentially replicate the same mechanisms that underpin Bitcoin, but you just swap out, again, kind of like how you swap out the problems that seem to be difficult in cryptography. We swap out the proof of work for a quantum proof of work. And it turns out that there is a way to do this using what's called coarse grain boson sampling. Is anybody here like studying quantum computing or quantum physics or? Nice. Okay. Nice. Are you familiar with this, with boson sampling at all? Okay.
But I know what a boson is.
Yeah. Okay. So yeah, let's go with that. So the idea here is essentially you can, okay, so the goal is we're trying to create a new proof of work. Okay, so a proof of work is essentially miners trying to solve SHA-256. And essentially they have to keep trying different nonces in order to get the hash to work out. And that's the work that they're expending. And we want to substitute that with a quantum problem. And so we can use this idea called, or this problem called a boson sampler, where essentially you can think about it as like, have you ever gone to the fair and there's this like board that's like a triangle, has a bunch of pegs in it, and you drop in, let's say like a ball, and it kind of pings back and forth between the pegs, and then it lands in one of the bins at the bottom, and you're trying to, like, let's say if it gets a certain bin, then you win a prize. So a coarse grain boson sampler is essentially the same idea. You have this, it's like called like a Galton board, this with different pegs, and you drop in like a boson, and instead of like pegs, you have like beam splitters, and this will decide whether it goes one direction or the other direction based off of some quantum state. And eventually the boson will land in some bin at the end of it. And in this idea, the quantum miners are trying to guess essentially the distribution of what where the bosons lie after they've been put through this board. Because yeah, as we kind of repeatedly put in bosons, they end up in this bin 5 times, and this bin 3 times, and this bin 10 times. So it forms a probability distribution, and these miners are trying to estimate that by performing this boson sampling proof of work over and over again. Yeah, so that's the idea there, and essentially we can keep the same workflow that that Bitcoin mining uses today, but instead we just swap out all of the SHA-256 stuff and then put in boson sampling. So transactions create a network, it gets broadcasted, a new block is sent to every node of the network, and then all the miners try to essentially, oh wait, sorry, this is the traditional proof of work. Yeah, but all the miners try to solve the cryptographic hash function. And in quantum proof of work, you have the exact same flow, but you have people trying to compute this probability distribution. And then the really cool thing about this is that it's actually able to be classically verified. So we can each verify that a quantum miner performed the work on our classical computers, which is really, really powerful. And what this does is essentially it makes Bitcoin quantum proof, or at least the proof of work quantum proof. Once you also add on the post-quantum digital signatures to secure private public keys, right? So this is how these two things come together. Now we can actually have a fully fledged Bitcoin or cryptocurrency system that uses post-quantum cryptography to generate our private keys, and then also have a quantum safe proof of work so that no quantum adversary is ever able to overtake the network. So pretty cool. And it turns out that's also a lot more efficient. So these boson samplers, they fit on a desk. And yeah, they just take like exponentially less energy than these large data centers with mining rigs powered with ASICs. So it makes Bitcoin viable again in terms of like energy efficiency and in terms of green or I guess being like environmentally friendly. So that's also really cool. Okay, another application that we're looking at is securing Ethereum. So yeah, we've talked a lot about using this cryptography to make to make blockchain safe, and then this idea for layer Q is essentially the manifestation of that. So like we've looked at building a bunch of different libraries that use Falcon, which was one of the NIST standardized algorithms, and then building a bunch of software libraries for developers to build their own applications with. And so we have like our own transactions that can be broadcasted across Ethereum that are using Falcon signatures. And then we built our own like client, which is how people can interact with the blockchain. And then we've used this idea of aggregate signatures in order to compress all of these really expensive post-quantum digital signatures. And some interesting use cases that come out of this is that you can have now very plausibly you can have a quantum safe savings account on Ethereum, where you have one version, we have one wallet that uses elliptic curve cryptography, but it's quantum vulnerable, but it's probably cheaper to use because there's all the infrastructure available for it. And then you can also have another wallet that's secured with post-quantum cryptography, and you can think about that as your savings account, where you don't transact from it as much, but you know that your money is safe there. There's also this idea of using quantum safe multi-sig wallets. Multi-sig is where you have to have multiple signatures sign off on making a transaction, and then you can essentially have like a quantum secure wallet, and then, you're gonna just make sure that at least one of your quantum secure wallets signs off on it in order to authorize the transaction. And then we can also do things like having there's all these ideas for like staked ETH and wrapped ETH, and we can have some sort of quantum ETH idea where there's like a one-to-one backing between Ethereum and its quantum counterpart. And as there's more developments in quantum computing, hypothetically the premium on that quantum-backed security, that quantum-backed Ethereum, would increase and would accrue more value over time. So it's an interesting potential financial instrument. And then the last kind of use case that we're looking at for applying this cryptography is in CBDCs, so central bank digital currencies, in an effort to build quantum money, essentially. So quantum money is a scheme that essentially creates and verifies banknotes that are resistant to forgery. And it's actually an idea from way back in the 1970s. But the idea is essentially that these digital signatures that we've talked about this whole time, they're analogous to a security thread on a bill. So like, if you get like a really large bill, let's say 1,000 NT, or maybe it's $100 US bill, some people like look at it in the light and like see if there's that seal, the security thread, to make sure that they know it's a legitimate bill. And digital signatures essentially provide the same mechanism for us in this internet world, where we can verify that certain coins or dollars were issued by a central bank. It's a central bank digital currency, not a replicated digital currency. And essentially, you can have this idea where you have this quantum minting press where maybe use post-quantum cryptography to mint and digitally sign all of these different banknotes or bank tokens. Or maybe you in the future also have some sort of quantum way to do this. But essentially trying to think about how can we update our current money system? Well, one of the ways to do that would be to establish some sort of quantum minting press in order to be quantum safe in the future. Yeah, and the history of quantum money also dates back to the guy who invented Shor's algorithm, Peter Shor. So it all kind of comes full circle. Shor's algorithm is the problem that he is be able to exponentially solve the discrete logarithm problem. And he was also thinking about, okay, well, what kind of implication does this have on society? And way back when he foresaw this future where quantum would be at the heart of every financial of all financial infrastructure and banknotes. So yeah, that's the takeaway. This is a bit more of a degen. take away, but in crypto, there's this thing called rug pulls. It's essentially where like a token just collapses because of some fraud or some bad actors. And the argument here is that quantum is going to be the biggest rug pull of the century. It'll destroy all of our blockchain and potentially even financial infrastructure. And what I like to always say is it even money if it's not quantum safe? So yeah, thanks very much for listening, and that was fun. Cool. Yeah. Any questions? I know it was a lot, but hopefully you guys came away with some interesting ideas. But yeah.
Maybe on a high level, how does it work that you can compute with quantum computers and be able to verify with classical computers? What's the science behind that?
Yeah, that's a really good question. So yeah, okay. So the idea is that in this boson set in this. Okay. Yeah. Okay. Let's use this. Essentially, what the quantum miners are trying to do is like feed enough bosons into this boson sampler and generate a probability distribution, or like actually it'll be like their sample distribution for the for where the kind of the bosons lie after some encoded quantum state. And the quantum state is defined off the block information, so it'll be always unique. And people can verify this essentially by saying, like, we know what the quantum state is, and then we can actually just kind of solve for we can verify that this distribution is within a range of what we expected it to be, but it's really hard to actually compute that distribution initially. Yeah, it's kind of like the same problem where it's really easy to verify that a hash checks out, but then it's really hard to reverse the hash. Yeah. Okay. Any other questions? Okay. Well, yeah. Thanks so much, guys. I really appreciate your attention. And yeah.
Last question.
Yeah.
So you have quantum proof of work for Bitcoin, but for Ethereum proof of stake, there isn't. Like, you don't really need it, right?
Yeah, you wouldn't need it, but I think you would rather have like signature aggregation, because in validator committees and like in a proof of stake, in proof of stake, you essentially have people staking, like putting up money that they're willing to lose if they act, with bad incentives. And what their job is just to verify that this block checks out, execute all the signatures and transactions, make sure that they all work. And then once they do that, once they verify it, they sign off on it, and then they pass it to the next validator. And these validator committees typically consist of a few thousand, and in the future, they'll likely consist of a few 100,000. And so in this process, a lot of blocks are being signed by all the different validators. And so you would have, this like huge database of signatures attached to a single block for all the validators, and then you would want to use some sort of a signature aggregation. So that's actually what Ethereum is doing right now. They're doing DLS signature aggregation in order to help compress that. Yeah. Mm-hmm.
When do you think we'll have a quantum money?
Yeah, that's a good question. I mean, we're trying to build it. We're trying to build it at BTQ. But yeah, there's still, I think, a lot of, but there's like, I think it's like, it's one thing to have built something, and then another thing to have it be adopted.
Yeah.
According to these like timeline projections, it could possibly be within like 10, 15 years. Yeah, I guess it all depends on how fast things progress.
Is there like a chicken and egg problem where like before you have quantum technology, you don't really need quantum money, but then by the time it's ready, you want to have that ready.
Right. That's a great question. And actually, it's not a chicken and egg problem. With quantum computers, kind of the classic attack would be to harvest all the data now and then to decrypt it later. And so quantum, there's already governments and companies around the world who are harvesting information today in an attempt to decrypt it once they have a sufficiently powerful quantum computer. And so, yeah, it's actually like a priority by everyone to start using PQC as soon as possible. And that's why NIST has started this competition kind of, yeah, all the way back in 2016. And they recognize it. It's just companies have a really hard time justifying the expenditure related to swapping over their cryptographic infrastructure. Because it's very like cryptography is kind of like plumbing underneath the city. It's kind of like the pipes, the piping of a city, and it takes a lot of work you need to dig in and then change everything and then put everything back on top. So that's probably been like the biggest bottleneck. But it seems like companies now are taking this more seriously, especially now that the US has standardized these algorithms and there's certifications that US companies are getting. So FIPS type certifications that essentially saying, this product is quantum safe, certified by the national government, use it. Yeah.
What's the intent to make a message? Like when you send a message, you send a statement.
So what's that? Yeah, okay, so the whole blockchain mechanics, like the whole transferring of assets, that's still using the typical cryptography. No quantum states are happening there. It's only for the proof of work. It's only for so maybe what you're asking is how does, because I said like the Gallatin board, essentially the Boson sampler, that's defined off of block headers, and so there's information from the transactions that are used to define this quantum state that encodes this boson sampling problem.
If you're entangled with these two things and then you try to see it, it will collapse and you will.
Exactly. Yeah. Exactly. Yeah. Yeah. Exactly. Yeah. So yeah, there's no quantum states associated with the transactions themselves. Yeah. Mm-hmm.
Could it be?
I don't know. That's really cool.
Because if you do that, well, it gives like the only problem would be how to prevent the happen. Know what I mean?
I know what you mean. I think there would also be a problem of how would you know like what the transaction is, because it would be held in a superposition, and then it would probabilistically collapse to one another. But it sounds like a really cool, yeah. Yeah. It also sounds like a really cool like lottery problem, because yeah, you could encode, this lottery win into a quantum state, and then so it has a probability of, yeah. But yeah, did that answer your question? Okay, cool, thank you.
Yeah, dumb question.
Yeah.
In the beginning of the slides, you were talking about quantum being superposition.
Mm-hmm.
And being able to be at position 0 and 1 at the same time.
Yeah.
I actually don't know what that means, to be able to represent 0 and 1 at the same time.
Yeah, so it's you can think about it as it's just a number in between 0 and 1, and it has some probability that it's going to collapse to 0 or 1. Yeah. So it's just a probability more so. Yeah. Mm-hmm.
So what is the relationships or similarity between the BTQ and zero computing?
Oh, yeah, really good question. Yeah, thanks. Yeah. So we talked about how ZK can be used to help, compress these post-quantum digital signatures. And so what we did at BTQ, essentially for the past 3 years, was we built a bunch of ZK tools and products in order to achieve this. So we built our own ZK programming language in order to write these programs. But then using that ZK programming language, we built our signature aggregation service, which compresses all these post-quantum digital signatures. And then we've also been exploring hardware, big reason of why we're here in Taiwan, looking at how we can accelerate these post-quantum ZK operations on ASICs, essentially. And yeah, essentially when it came time to deliver those products to the market, we realized that we were paying out of our ear in AWS costs. We were paying $7K US just to develop and test these post-quantum snarks. We weren't even serving customers. And so we realized there was this huge gap in dedicated infrastructure for generating zero-knowledge proofs. And that's what zero computing is focused on now. It's dedicated infrastructure for zero-knowledge proof generation.
You mean the infrastructure means the hardware or software or knowledge or education?
Great,
workshop, what kind of infrastructures?
Yeah, so it operates, it's kind of like a middleware in between, and it's a middleware that sits on top of hardware. It's software that sits on top of hardware. So essentially what it does is it looks at how can you orchestrate a cluster of GPUs, for example, to generate a proof most efficiently. It also looks at how do you actually virtualize a compute instance in order to be tailored to a certain proof request. So like the classic example being on AWS. When you interact with AWS, you want to rent an instance there. They give you a general purpose EC2 instance. By definition, general purpose is used for everything from building websites to hosting web apps, doing machine learning, and it doesn't offer any customizations for certain workloads. And because ZK is so expensive, we actually want to be able to virtualize instances or virtualize hardware based off of certain requirements to be essentially customized for a zero-knowledge proof request. And what I mean by virtualizing is like AWS has a huge data center, like multiple data centers. And when they give you an instance, they're essentially, it's called virtualizing. They're carving out a part of a data center to give to you to use. And so what we looked at doing was, how do you actually perform that process? This is why I'm saying it's software sitting on top of hardware. How do you actually virtualize a server so that it can be most optimal to generate a certain zero-knowledge proof on a case-by-case basis?
So how many? So it's founded and from 2024, just this year.
So we started building zero computing kind of within BTQ last year in 2023. Yeah.
Okay.
Yeah.
So already any kind of like a proof of concept or kind of some prototype?
Yeah, we do. Yeah, exactly. Yeah. And
so it's will you have client or your solution provider, or will you sell the solution to, it's what kind of user or client for your solution?
Exactly. So because these ZK EVMs have emerged in order to generate proofs for all the user transactions, these are the customer profiles we look at. So we target, like, our customers are ZK EVMs who generate
company.
Yeah, companies. Exactly. Yeah. So we don't actually interact too much with users. We're like a B2B focus on companies. Yeah.
So at the beginning, when you're in BTQ, you're focusing on several issues on quantum computing or post-quantum cryptography. However, recently in zero computing, it's not much quantum technology that you're focusing on, right?
Exactly. Yeah. So we just took the ZK from helping scale post-quantum cryptography, and we built a more generalized service for that.
Okay. So how many people or the member in this new startup or company? Zero computing.
Yes. So there's myself plus 2 engineers who are working on this
in Taiwan or remote.
These guys are overseas in North America. Yeah.
So it's self-funding, or like you got funding from the
BTQ has
really?
Yeah.
Oh wow.
Yeah.
Interesting.
Yeah.
So because you're a middleware, so maybe you will have to work with like business clients such as the ZK EVM company, or maybe with some manufacturer or like Quanta or Foxconn or
Yeah, exactly. Yeah. So on the demand side, like our demand side customers would be the ZK EVMs. And then on the supply side, since we need to actually generate those proofs with hardware, that's where those types of relationships can come in. We aren't speaking to anyone right now. Right now, we use bare metal servers, which are widely available right now. But if we want to do any kind of more accelerated or customized hardware, then yeah, we would look at those manufacturing companies.
Yeah, sounds super nice. So what is the demand side? Is it high demands, or like the peak will not this year, maybe next year, or like upcoming few years, or
Yeah, so yeah, demand is increasing. There's a really good website. Actually, I haven't seen this since L2 Beat. There was a recent dip in the market as a result of the war, or I shouldn't say the war, but like Iran firing missiles at Israel, and that caused this dip here. But this is activity on layer 2s, so these roll-ups that help scale Ethereum. And you can see that the transactions per second have, since 2023 even. I mean, this is all okay. Let me go max.
Yeah.
So yeah, okay, no problem. Yeah, no, I've never seen that actually. So these are all the transactions that are going over these layer 2s. I should note, not all of these are ZK based or use these proofs of knowledge. There's some optimistic rollups like Arbitrum and OPNet. OP optimism. I don't know what this is. It's all three apparently. But base is they use ZK, and ZK Sync, and some of the other ones use ZK. So increasing demand in a lot of these optimistic, this maybe outside the scope for a little bit of people, but a lot of these teams are starting to look at using ZK. So they're moving towards zero knowledge proofs, which is nice. And I should say another really nice tailwind is this whole AI thing, which has swept the world. But essentially, a lot of people are looking at how you can decentralize AI, put it essentially, what if I'm able to run like Llama 3 on my computer? Can I establish a connection with somebody else in order to provide them with their inference service, so that they can interact with the model using these like Web3 principles? And then that's also something that we're looking at now with zero computing is how do we repurpose our infrastructure to do that? And I think it makes a lot of sense. The things that we're concerned about is essentially ensuring high availability, reliability, fault tolerance. These are very fundamental kind of like product consumer principles that we need to follow in order to deliver these services. So that's another area of interest.
Okay. So any question? Yeah. Okay. Yeah. Actually, I would like to have these types of new topic sharing, because I really enjoy some types of sharing that maybe more than 50% is I didn't really understand. However, we have a recording, and we will share it on NTU Cool and also on YouTube. So if we want to review or like revisit or rewatch the sharing, I believe we can do it. So any question?
可以问大家一个问题吗？这样我好奇大家做 DK 零知识证明的东西，好奇什么？
有啊，刚刚有一些啊。
对这方面的主题会有兴趣的东西。
有啊。
好，谢谢。
OK，好，还有没有任何问题？好。 OK， 好，没有的话呢，我们今天就是 Chris 嘛，哈。好，那我们今天一样呢，把多余的时间留给大家，可以私下 Q&A。然后之外呢，我们也欢迎大家透过剩余的时间来做pre 分组讨论啊。如果你还没有一些分组的想法，或者还没有确定的，欢迎透过实体的课程的时间来跟大家做连结。OK， 好，那我们再次掌声，谢谢 Chris。
Yeah, so, thank you, thank you, thank you, thank you. Thank you so much. I also want to say BTQ has an internship program. If any of you guys are interested in working there, I can attest it's a really good company. A lot of really smart people. So if you're interested, feel free to reach out to me. My email is chris@btq.com. Maybe there's another way. I can share some information later, but if you're interested, feel free to reach out. And always looking for, and NTU is one of the best schools in the world. So looking for young talent. So yeah, thank you for your time.
Yeah, thank you. Yeah, it's remind me that when I watched Steve Jobs talks back to 1990s or 1980s in Stanford, it's just like this kind of classroom, and everyone is just what? And he's trying to imagine what's the solution about Google Map and the future computing on mobile, and everyone is like, what? And also I can imagine that the early 90s, the crypto punks, for example, like Nick Zappo, when they're sharing some news about some development about like eCash or like early days trials about blockchain. I believe it will be like that. Everyone will be like kind of a lot of content is like a little mysterious.
Right.
However, I believe like as time goes by, we will figure out that this is the future. Okay, like post-quantum or like ZK and the new development solution. Yeah,
Let's build it together.
yeah. Thank you.
Thank you.
好，所以大家如果有问题，还是可以私下交流。好，那我们的录影呢会上线。好，那剩下的时间大家可以看一下分组，大家还有没有什么其他的问题？好 ，OK，
Have it.
好。
Let me see.